Good morning, everyone. It is a pleasure to be here virtually with you, and I want to thank the organizers for inviting me. Today, I will present collaborative work on combining hierarchical approximation with importance sampling. This work has been done with many of my colleagues and friends through the years, so it's my pleasure to bring it to you today. Here's my brief overview of the talk. So we will begin by the introduction, and then we will showcase the techniques in different model problems. Let's begin with the building block of control variates and importance sampling in the context of Monte Carlo. Control variates is the idea behind hierarchical sampling like multi-level, multi-index, Monte Carlo methods. Just to keep it in your mind, I recall it here. Let y be a random variable. Instead of approximating the expected value of y with Monte Carlo directly, sampling from y, we instead represent the expected value of y by this summing or subtracting of the same term, namely beta times x. And you see here that there's a cancellation and we still get the same value, expected value of y on the right-hand side. Here x is a variable that is essentially cheap to sample and is correlated with y. In fact, sampling from the right-hand side, taking these two terms in an independent way, will provide a more efficient Monte Carlo approximation than just using Monte Carlo on the left, if this inequality holds, where epsilon here is the relative cost of, is the relative variance, that is the variance of y minus beta x divided by the variance of y, and eta is just this other relative variance cost. What is important here to make this approximation efficient are these two terms, epsilon and theta. Epsilon, as I said, is the potential for variance reduction that this technique offers, and the theta is related with the cost of employing this technique, namely the cost of sampling jointly y and x to create this sample is here marked by 1 plus theta times the cost of simply sampling y. All right, and in the same way we represent the cost of sampling x alone in terms of sampling y alone by the same theta here. So this technique will be efficient whenever this happens. Namely, again, x has to be cheap and sufficiently correlated to make epsilon small and also theta small. If that is the case, well, the first term essentially is governed by square root of epsilon, and the second term is governed by square root of theta. What is the other ingredient that we're going to be touching upon? Well, that is importance sampling. And what is importance sampling? Well, it's a change of measure. Essentially, we multiply and divide by the same quantity, keeping the expected value unchanged, but changing the variance in that process. So now we actually track the probability measure that is used to compute the expectation, and we represent the expected value of y, which is what we wanted, as the expected value of y times paradonic-Odin, a likelihood factor here, but now under a new measure is q, okay? And instead of using Monte Carlo on the left, we use Monte Carlo on the right, where our new variable essentially is the product between y and the likelihood factor. Our new probability sampling measure is q. If we choose q optimally, then the minimum variance we can achieve in this process is given by this formula. And essentially here you see two things. One is this square here, and the other is this difference here. Well, this method is going to be effective when either this part is small or this part is small. When this part is small, well, we essentially mean that this coefficient of variation is actually much larger than 1, or that y essentially had a constant sign. Essentially, for example, y to begin with was a non-negative random variable, and in that case, the second term here will vanish, right? So in both cases, you have potential to improve using importance sampling. The only way to actually get actual improvement is to see whether this inequality holds. And this inequality holds for this inequality to hold, actually, you need not only the variance reduction to be effective, but also the cost of applying it not to be too large. And this again is governed by this theta factor, which is essentially representing the relative cost of sampling y times the likelihood factor under Q star with respect to sampling y under P. And now that we have these two ingredients, the control variates and the importance sampling on the table, we discuss how to combine importance sampling with hierarchical sampling. And for that, I have to move on to hierarchical sampling. And that is, mostly known as multi-level Monte Carlo due to Heinrich and Giles. Here, I don't need to repeat what Professor Nobili already told you. You write these differences among levels of approximations, telescopic sums. Your approximation is based on this sample across levels. You can get, based on this hypothesis of weak convergence, strong convergence, and explosion of the work, different regimes for the multi-level optimal convergence. And again, depending on whether the strong rate is larger than the exponential growth of the work, well, then we get the optimal case, which is 10 to the minus 2, up to the case where the strong rate of convergence for the variances is less than the exponent for the work. And in that case, you still get something better than Monte Carlo. We talk about importance sampling, right? And I want to make a small distinction for those in the audience that already know Monte Carlo, multi-level Monte Carlo, and unbiased versions of that, the unbiased versions of multi-level Monte Carlo where you actually play importance sampling across levels. This is not what we do here, and we're not going to discuss it. I'm happy to discuss this with the questions, but it's not something that I will be touching in this talk. Several questions can be and have been addressed with respect to multi-level Monte Carlo, how to choose a hierarchy for approximation, how to efficiently and reliably estimate these unknown parameters, which are the variances, which are very crucial to choose the number of samples across levels, and how can we do better, specifically for dimension D larger than 1, to address these inequalities here if some mixed irregularity is available. All that essentially is discussed here in these references and in the multi-index that I will be briefly touching upon. But before that, let's combine importance sampling with multi-level Monte Carlo. Let us introduce then importance sampling in the multi-level Monte Carlo telescopic identity using a sequence of importance sampling measures that we denote here by nu L, and these probability measures will act on the pairs SL and SL minus 1 so that we approximate our expectation under P, right, of the exact quantity of S by an expectation under an approximate measure PL of the approximate quantity, say SL capital, in the following way. We just telescope, and we not only telescope the approximation of the quantity of interest due to discretization, say, but we also telescope with respect to the measures here. All right. So in this expectation representation, there is no yet coupling between sampling on the different levels, and that's why the nu L's bring. We will then sample together SL and SL minus 1 using the nu L joint measure, and I have to correct here using the corresponding likelihood factors, right? And the likelihood factor will be different in each case because I have to use the marginal distribution of nu essentially with respect to the PL and here the L minus 1. All right, so now we have these random variables, call it ZL, which are differences that encode not only the approximation of the quantity of interest, but also the approximation of the measure that we want to sample from. And the choice of this nu L, as you will see, is fundamental for this importance sampling combined with multi-level Monte Carlo to work. In fact, we choose the nu L's, or ideally choose the nu L's, in such a way that the computational work for the importance sampling multi-level Monte Carlo is minimized. In that sense, what we need to do then is to minimize the product of the variance of these ZLs times the corresponding cost of sampling the ZLs under the joint measure nu L's. And this is done for each of the L's right? And this gives us the optimal choice. Now, this optimal choice is ideal, and in practice is very difficult to obtain. Therefore, we get some proxies that eventually yield a computational advantage still when compared to non-important sampling, essentially multi-level Monte Carlo. Let's see the first example then, which is a hybrid and important sampling multi-level Monte Carlo for stochastic reaction networks. What are, in a nutshell, stochastic reaction networks? Well, there are time-dependent stochastic processes, written here represented using the Kurtz representation as a sum, right, of jumps corresponding to Poisson processes multiplied to the so-called stoichiometric vectors nu j that represent the different changes that occur in the system. With this kind of a representation, one can use modeling in biosciences, chemistry, Qs, and so forth. I can go forever with applications. The point here is that you can discretize this system with this. You see that there's a non-trivial connection between the actual value of x and these clocks that are used to stretch the time in the evaluation of these independent unit rate Poisson processes. So we can discretize this, and one method that is commonly used is the tau leap, where after including delta t steps here and some approximation, you get sum of Poisson random variables here. And as you can see, everything happens here on a bookkeeping basis, and the values of x are just taking values on a lattice. They're not continuous. They just, you are just essentially counting, for instance, the number of people coming into a queue, or the number of molecules of oxygen inside of a certain reaction, and so forth. And these new J's actually are tracking what happens when a certain reaction in the system fires. It could be that one person leaves the queue, another arrives with another kind of reaction, and so forth, right? So you're tracking essentially integer values. And although if you plot them on a larger scale, and like this green curve, the evolution may look continuous, actually, when you get to small numbers, you clearly see here the discrete nature of this evolution. All right, so I don't discuss this anymore, but I just wanted to say that this is a problem that is well suited for the combination of multi-layer Monte Carlo with important sampling. In fact, there's an issue here, and if you look carefully into the system, what you will see is that when you take the telescopic differences between corresponding discretization levels in multi-layer Monte Carlo, the probability of these two levels to be exactly given the same value at the end goes to 1 as delta t goes to 0, essentially with this rate. So specifically, what this happens is that if in multi-level Monte Carlo you're sampling differences to actually feed your level L, well, most of these differences will be 0, and very rarely you get something that is non-zero, which is precisely what you should address when you try to apply important sampling. This is what has bad consequences, right? I mean, again, sampling these levels becomes essentially a problem of important, of a rare event, and needs important sampling. The kurtosis explodes. Variances that you need in multi-level Monte Carlo become inaccurately approximated, and so forth. So here we changed essentially in some suitable way the measure to actually provoke more changes between level L and level L minus 1 with a very precise rate, so that at the end we can go from this work, right, and this explosion in the kurtosis and this rate in the variance convergence to less explosive kurtosis, a faster convergence rate in variance sense, and achieving then the optimal work versus accuracy that you can get with a multi-layer Monte Carlo in this setting. Actually, not only you can show it in theory, but you can see it in practice. here's a one standard example in this regime where you have some reactions, right? And you want to predict, say, the third component in the system, its expected value of the component 3 at final time. And then what you can see is that if we don't use importance sampling, well, the variance only converges like delta t. The kurtosis blows up essentially like 1/delta t. Observe here values up to 10 to the 3 in the kurtosis, which is extremely bad. But if you use importance sampling, you can actually increase the rate of convergence for the variance up to 1 plus delta, essentially, and you can see in this plot, while you keep a kurtosis essentially of value up to 6, which is essentially not exploding at all in comparison to the previous computation. This is just by changing the measure in the computations done with the Multi-Index Monte Carlo. And again, the optimal complexity is achieved. You can also show the plots and compare with other standard methods, and this method behaves better. Now we briefly mentioned multi-index hierarchical sampling. The main message is that multi-index is more effective than multi-level, particularly in large dimensions, provided extra regularity it can exploit. And the second part of the message will be, of course, that importance sampling can be used in this method as well, although I will concentrate my exposition just only on multi-level. So to understand quickly multi-index, please refer to this PDE motivational example, just one PDE with different directions in the X space, right? And one functional that we want to compute the expectations from. We may have, therefore, some different directions to discretize, say X or Y or Z. For each of them, we're going to use different discretization sizes, and this is where the multi-index name actually arises, right? Because we have the ability, as opposed to multi-level, to choose different discretization levels in different directions, and from there, create different representations for the desired functional S. And yeah, you can work in pretty general geometries using these constructions. They look similar to multi-level, but of course it has some complications because you now have to work with lattices, not just with levels. And well, you have to also show regularity from your mixed differences here to extract the advantages in the rate. And for that, you may have to refer to different type of assumptions that yield this mixed regularity. Some of them are discussed in the papers that are listed here, and I will not stop. So, but as a conclusion, then when you use these methods, essentially, you can actually face the worst direction and reduce essentially the problems to facing a one-dimensional type of hierarchical approximation and not a d-dimensional one. For example, remember in the multi-level, we have this nasty dependence on the D, right, in these inequalities. Now, if you go to multi-index, actually you can get rid of that. And you can verify that in actual computations. Here's a 3D computation with a stochastic random PDE, and you gain from multi-index Monte Carlo to multi-level in memory use and also in runtime for getting to a certain accuracy. And the more, the higher the dimension, the more you gain. In this case, you get from 10 to the -6, which is the worst with Monte Carlo, to 10 to the -4 dependence with multi-level, and 10 to the -2 actually with multi-index. So that's pretty dramatic since we are using the same finite element space. All right, so I mentioned different discretization directions treated in different ways. Well, of course, discretization directions do not need to be spatial. It could be time, or it could be even the size of a particle system. Indeed, we used multi-index Monte Carlo for stochastic particle systems with an eye on the application of simulating crowd flows. In that case, actually, one can get a substantial complexity reduction from here into here. The reference actually is in this multi-level and multi-index for Makin-Blasov. And just as a cool illustration of what one can do with the crowd flows, right? This is a simulation of a bunch of people escaping from a room. We use it, for example, to simulate best positions of obstacles to help the escape in this situation. Now, you can actually go beyond multi-index Monte Carlo by substituting the Monte Carlo quadrature by multi-index stochastic collocation using sparse quadratures instead. And then, provided the additional regularity that we characterize as well, you can produce more efficient computations. For instance, in this linear PDE with random inputs of elliptic type, we did the computations here with the case of 3 dimensions, right? And you see here multi-index Monte Carlo behaving as best as it can. And here you see a computation done with multi-index stochastic collocation. And you see that in terms of error for the same work, it outperforms dramatically the way multi-index Monte Carlo does. Now, multi-index stochastic collocation can be carried out into infinite dimensions as well. We have results in this direction, but of course, the talk is about something else today. And I leave you just with a couple of pictures of how we can actually do things in more general geometries, thanks to isogeometric analysis combined with multi-index stochastic collocation, doing better computations, right, getting better rates. Now, let's switch gears and see another computation with importance sampling combined with multilevel. This is in the context of optimal design of experiments, where we want to design how we acquire and which type of data we acquire in order to maximize the expected information gain from a prior knowledge on the quantity we want into a posterior knowledge that we get out of this quantity once we produce the experiments. Of course, these experiments are designed before any data is taken, so everything is synthetic, right? So what is the point here? Well, we make a model for our data that is going to be acquired. This data somehow is going to be generated out of a certain function that depends on a parameter that is going to be random, and then a design parameter for the experiment, plus some corruption of noise given here by Gaussian type of noise. And then in that context, you compute the expected information gain corresponding to a design parameter xi, right? And this is written in this way using Bayesian framework, right? Going from prior to posterior distributions. But mathematically, from the numerical analysis point of view, we see this as a nested expectation because of this factor, actually. And because of that, actually, we need to actually deal with a concentration effect that will ask us to use importance sampling. Intuitively, what happens is the following. If you design your experiments well, the more data you acquire, the more concentrated your posterior for your unknown parameter will be. This is beneficial from the sort of solution point of view. From the numerics, actually, this actually asks you to deal with a very concentrated integration, and you have to adjust to it. So how do we formalize this? Well, we again can rewrite our information gain, and we are not moving the design parameter here. So we take it out from the notation. We write here an expectation of this z of theta. This z of theta itself is an integral, and it contains here in this py another integral as well. So this could be actually rewritten in this way. So you have an outer integral here and another integral that is actually the one that concerns us the most, because fixed theta here, I have to integrate with respect to theta prime, and the function a of theta and theta prime produces this concentration that I was talking about. And to address it, we need to use a Laplace approximation in this setting to produce an importance sampling measure and combine it with multilevel for efficient computations. So again, summing up, expected information gains brings us to the problem of nested expectations. These nested expectations may contain terms that have measured concentration. This measured concentration is addressed by an importance sampling, together with the usual multi-level that will arise in the discretization of all these quantities. Of course, to get the proper results, you need to make assumptions on the accuracy that you have in approximation of these quantities and the work that is needed to produce them. That's fine. And then you actually produce different results. What I'm going to show here is an experimental setting where you have composite material with the 2 plies, right? And we want to acquire, to recover the orientational angles of the plies out of pushing electricity through different electrodes and designing the position of these electrodes for best recovery. So again, this is the position of the electrodes, right? The 2 plies, we don't know the alpha 1 and alpha 2 angles. We're going to, again, push electricity from one side to the other and try to choose the best possible position for these electrodes where we actually inject and we measure the voltages. And well, there's a best way of doing this. And I'm not going to discuss too much on that. The only point is that if you do this properly, you get a substantial improvement from the posterior without the optimization, essentially, and the posterior with the optimized design of the experiment. And you see that there's a much concentrated posterior thanks to the design, the optimal design here. You can generalize to an example here with 4 plies. And here I show you the computations, right? We first show you that, as usual, we track very closely the error that we want to have in our computations given by toll here versus the actual computational error, that is the error in blue. And once we do that, we compare different methods. And in this context, again, multi-level importance sampling using stochastic allocation comes out as a clear winner with a massive gain, essentially in computational work, for a reasonable engineering type of tolerance, as you see here. Until now, we saw examples where Monte Carlo and importance sampling were used to provide accuracy in our computations. Now, with multi-level discrete least squares approximations, Monte Carlo and importance sampling will be used to provide stability in our computations. Accuracy will come from best approximation of our projecting subspaces. So what's the problem? We have a PDE here, parametric in the input Y in red, and the solution U actually is not exactly what we want. We want to recover a functional Q applied to the solution U as a function of this input variable Y. That we call F, and we want to recover, therefore, F of Y, possibly with multivariate polynomials or other families. This could be applied in inverse problems and other things. So we want to record, as I said, the function F. We will project it over a subspace that we index by this set of indices lambda. This set of indices lambda may look like this, and each of these red points here corresponds to a monomial, if you think of polynomials, right? We use downwards closed sets, that's technical. But what do we do here? Well, pretty much like in machine learning, we sample independent endpoints according to a distribution for the points Y, right? Based on these points Y that may not be sampled by the measure we wanted to estimate the error by something else instead, and there you see already some important sampling in action. We then find the best sort of discrete least squares regression of F on that subspace based on these M capital samples and using properly the weights W here. All right, so this notation again is such that the expected value of this discrete L2 norm actually corresponds to the exact L2 norm we wanted to approximate, and then solution of this quadratic problem is written in terms of simply a least squares problem whose matrix, of course, is this Gramian, and the right-hand side is given by this. All right, this is pretty standard. What is not so standard is the theorem of Cohen and Migliorati from 2017, and this relates to other work with Cohen and Davenport and Leviathan, that says essentially that to have stable recovery in that projection, you need sufficient number of samples. How many samples? Well, this sampling inequality tells you how many. And the key point that connects to this subspace lambda, V lambda, where we're projecting on, is this quantity, K lambda W, where W connects to the weight, and this lambda connects via these functions, right? That were the basis functions for the subspace that where we carry the projection, right? This quantity actually is the one that will connect the subspace and the need for samples to get a stable recovery of it. So indeed, if we substitute this inequality 10, this gradient that we're used to solve the least squares problem is close to the identity, so close that actually we can recover all these best approximation results. You see that here, the distance between the F and the discrete L2 projection is bounded above by something that is connected entirely to the subspace, and that's what I said, the accuracy comes from the subspace. Similar here in L2 and so forth. And the good news actually is that Cohen and Migliorati suggested already a way to optimally sample so that this K lambda that we were discussing before becomes actually the cardinality of the number of basis functions we need to span the subspace where we work on. And in that case, essentially the number of samples up to the log factor becomes linearly proportional to the dimensionality of the subspace where we project on, which is optimal. Okay, this is great. We have available sampling algorithms that are efficient from this optimal distribution. We have to be careful though that if lambda is not known a priori and you need to do some adaptivity to find it, well, you may need to use a near optimal distribution that is independent from the lambda. Otherwise, you may have to, for example, everything from scratch every time you add new functions to the projecting subspace. Now, if you want to go to multi-level in this context, of course, you have to assume that there's some sequence of say polynomial spaces, for example, that will provide the required approximability for the function f, right? And for each of those, we have to satisfy this sampling inequality, of course. And we also have some kind of discrete approximation of the PDE solution so that actually we have convergence in that way as well. If we have these two ingredients, right, the approximability with respect to the y and the approximability on the PDE, then you can create a multi-level formula where we actually approximate the function f by this formula that is first written in terms of a multi-index, which is the most natural way of doing it. And then when you sum up with respect to one of the indices as a multi-level formula. And what you see here essentially is that you have a projection acting on a difference between solutions that corresponds to different mesh sizes. And what's the point here? Well, you're going to, in this setting, you're going to use a coarser and coarser projection acting on finer and finer solutions here, which means that you're going to use less polynomials to represent the differences that come from the more costly, deeper levels. And why is that so? Well, because the difference in the more costly, deepest level is actually tending to zero by consistency of the PDE approximation. Okay, that's technical, but what is the bottom line? Well, the bottom line is that if, again, you have approximability assumptions in the way I said it, and the work is also estimated by some kind of explosion in the rate, then given, again, approximation over these polynomials, right, with a certain rate in L infinity, certain rate in L2, you have given some sequence of spatial discretization, some sequence of polynomials, in this case for approximability, keeping the sampling inequality. What do we have? Well, we have a result that says that multi-level will work in this context, will give you essentially base approximation properties of what? Well, you will get essentially the work corresponding to the worst of the possible rates, not the sum as you will have in a normal single level case. In this case, you will face the worst being, say, the polynomial subspace or the PDE approximation. And that actually is well confirmed by numerical examples as well, where you actually control the regularity of the coefficient here in this PD. And then again, you observe an advantage that corresponds to the theory between the multi-level method and the single level method in different dimensions and different kinds of regularity. So what's the conclusion? Again, we have derived this multi-level discrete least squares method that serves to reconstruct output quantities of interest of random PDEs. And this is, again, an example where importance sampling works. But in this case, the use of importance sampling was pretty subtle. It was done to have a stable recovery, not to provide additional accuracy. To conclude, we will see something that is neither multi-level Monte Carlo nor importance sampling, but is no less exciting. This is ongoing work on stochastic optimization. And here's the setup. We want to minimize a function f here, capital, a function of psi, which is our decision variable. And this f is not given explicitly, but it is given through an expectation of some little f that we have access to. Okay, this little f actually depends on a random variable theta that we are able to sample. This f capital is assumed to be L Lipschitz and mu strongly convex, right? So uniqueness of the minimum is not discussed here. A standard method from the literature is stochastic gradient descent, where we sample the theta, right, out of the distribution pi. We take a step of this kind, right, with a learning rate, or certain step size that is chosen properly decreasing, and then we converge towards the optimum. Zillion applications, no need to stop there. What do we do here? With multi-index, with multi-iteration stochastic optimizers, we denote mice, where we use control variates for estimating mean gradients in a hierarchical fashion. Now, this hierarchy is not done with respect to discretization. This is a fundamental difference with multi-level. Mice constructs a hierarchy out of previous optimization iterations and sample gradients that we already have from the history of this path of iterates. And we want to do this to save computational work and to keep an eye and keep a control on the relative precision on the statistical error of our mean gradient, right? So the mean gradient is here, our constructive estimator is here, and we want to control this difference in L2 sense in comparison to the actual unknown norm of this desired gradient up to a factor here, epsilon, that is given, right? And we keep constant through the iterations. This relative control, and it's already known in the literature, right, yields exponential convergence with respect to the number of iterations. What we did in this recent work, this in arXiv, we developed sharp convergence rates with precise constants in terms of the total work, not just the number of iterations, but we can actually use this multi-iteration construction to save on the computational work. And the good news is also that this estimator can be combined with most of the first order of stochastic optimization methods available, for example, stochastic gradient descent, or the very popular ADAM that is used in machine learning. So what is a multi-iteration stochastic optimizers? First, we discuss the estimator itself. Okay, so the estimator is, if you just look at the simplest possible ways that you can have it, where we keep essentially all the information of the previous history through the iterations, it looks deceivingly close to multi-level, right? The problem is that you get confused because you have this structure of averages, right, and differences, but the differences are done across a path of optimization, and the best, I think, is for you to see it in a pictorial way. So suppose that we start our iteration with this method in X0, we take M00 samples, right? And out of this, we decide, just for example, by taking an average of the gradient of these M00 samples, we decide to move to X1. When we are there, we actually take M11 samples at the point X1 of the gradients, sample gradients, but we also increase a little bit the amount of gradients that we sampled at M00, so that we can keep an eye on the differences between these gradients evaluated at X0 and X1, and this will keep us well informed and again control the variance of the gradient estimator, so that we now decide to move to X2.
And when we do that, again, we take more samples as x2, we increase the number of samples at x1, and we increase the numbers of samples at the x0, right? This in a very controlled way to minimize the work and other details that I cannot tell you now, but now we move to x3 and so forth and so forth. At some point, it may be beneficial to say, okay, some part of this old history is not longer useful anymore, and we restart the procedure or we do other things. In this context, we can show several results. For instance, the strong convergence with respect to the number of iterations and, most importantly, the numerical complexity in terms of the number of gradient evaluations and the desired accuracy toll. So here you see the strong convergence result, right, with something that looks very familiar, but with this addition of this epsilon that controls the relative error, statistical error in the gradient. And as I said before, we have this kind of result. If you want to reach the neighborhood of size toll around the optimum, well, you have to pay an expectation, the cost that is like this. This is a leading order term, essentially, that connects to the toll, like toll to the -2, and then constants that are very well determined in terms of the assumptions that we make on strong convexity and Lipschitz constants. And this is the initial error, of course. So that is very clean. We are very happy with that. We can actually show through numerical examples that these theoretical bounds actually represent really how the method behaves, and the method actually outperforms stochastic gradient descent in terms of number of gradient evaluations quite substantially. If you go to non-convex examples like the Rosenbrock function, this method still works well and even competes with the Adam in that context. I mean, we really are using Adam as well, because we combine Adam with this multi-iteration stochastic optimizer based on the mice estimator, and we obtain, again, interesting savings in computational time and evaluation of gradients to achieve a certain tolerance. We went all the way to try this with logistic regression examples as well. In particular, this set contains 11 million data points, and there we have a finite universe of data, and we compare with very well-known methods in the literature. And this very first sort of code that we have, that is not optimized in any ways, is behaving quite favorably already in terms of number of iterations to achieve a certain optimality gap, and also in terms of the runtime. So that's very, very encouraging, and it has us all excited. So keep it in mind, right? This is not multilevel Monte Carlo. There is no discretization with respect to certain parameters, right? So there's the same, the hierarchy is just done with respect to the history. We reuse, and this is very important, information from previous iterations, and we do the decision on sampling adaptively to keep this relative statistical error control of the gradient with minimal work. It is very advantageous for big data, or essentially cases where you don't have a finite universe of data as well. Combines easily with other first order optimizers like Adam, SGD, and many more. And we have some theoretical results to back it up. And finally, the extensive numerical experiments confirm the gains that we expected. This is very exciting. As a wrap up of the talk, I mentioned today important sampling combined with multi-level and multi-index methods. And we saw through several archetypes that we can get substantial gains when we use these two techniques together. The specific examples we addressed were the computation of expectations, then nested expectations in optimal experimental design, right? Then regression that connects also to machine learning in general. And finally, we touched these multi-iteration stochastic optimizers. In all of this, there's much to do. So I leave you with that door super open. Thank you so much. Ευχαριστώ πάρα πολύ. And I leave you then with some important sampling references to other multi-level works and a list of our references as well.